Hello everyone. I would like to thank the organizers for inviting me to give a talk in this conference. The title of my talk is Volume Conjecture, Geometric Decomposition and Deformation of Hyperbolic Structures. This talk is divided into two parts. In the first part, that means this video, I will first recall the definitions of two quantum invariants for lengths and phi-manifolds. I will use the scheme-theoretic approach to define the invariants, and this approach is purely combinatorics. After that, I will discuss how these combinatorially defined invariants could possibly be related to three-dimensional hyperbolic geometry. Finally, I will mention my recent results on this subject. All right, the first thing I would like to do is to recall the definition of the Colored-Jones polynomials. To do that, first, we define the Kaufman polynomial of a knot as follows. The Kaufman polynomial for a knot K with a plane diagram D, denoted by the bracket of D, is divided by the following rules. The first rule is the Kaufman bracket scheme relation. Given a plane diagram, whenever we see a crossing in this form, we resolve the crossing in these two different ways. Then we put two formal parameters, t to the power 1/4 and t to the power -1/4, in front of these two resolutions. After we resolve all the crossings, we will get a collection of diagrams consisting of unknowns which are unlinked with each other. The second rule basically says that we replace each unknown with the vector -2t to the power 1/2 minus t to the power -1/2. At the end, we will get a Laurent polynomial in t to the power 1/4 with integers coefficient. To show that this construction gives us a knot invariant, recall that two knot or link diagrams represent the same knot or link if and only if they are related by a sequence of Whitehead moves, as shown in these pictures. By direct computation, one can verify that the Kaufman polynomial is invariant under the second and the third Whitehead moves. For the first Whitehead move, it turns out that the Kaufman polynomial of a diagram with a twist is equal to this vector times the Kaufman polynomial of the diagram with the twist removed. Similarly, if we twist it in another direction, we'll get this equation. In order to remove the change under the first Whitehead move, recall that the White number omega d for an oriented diagram D is divided to be the number of positive crossings minus the number of negative crossings. In particular, the White number for a knot diagram is actually independent on the choice of orientation. This is because if we reverse the orientation of a diagram, we will reverse the direction of both arrows, and a positive crossing will still be a positive crossing after the change. From the first equation, we can see that from this picture to this picture, the White number decreased by 1, and we obtain an extra factor -t to the power 3/4. This observation leads to the following definition of the Jones polynomial. The Jones polynomial JKT is defined to be the Kaufman polynomial of the diagram D multiplied with this factor raised to the power -1 number of D. And one can show that this polynomial is indeed invariant under all three Whitehead moves. Next, we want to generalize this construction to obtain more knot invariants. To do that, we interpret these two equations as follows. There exists a so-called twist operator T acting on diagrams by inserting a twist. And this equation basically says that this diagram is an eigenvector for this twist operator with this particular eigenvalues. Therefore, generalizing this construction is the same as finding all the eigenvectors for the twist operator T and the corresponding eigenvalues. So we let D be a diagram of K. For any positive integer n, the nth Carter-Jones polynomials is divided by JNKT equal to the Kaufman polynomial of something times a factor raised to the power negative wife number of D, where this En is the closure of the so-called nth Jones vector projector, which is a linear combination of diagrams. Let me put two remarks here. First, the nth Jones vector projector is the eigenvector of the twist operator with this particular eigenvalue. And that's why we put this factor here and raised it to the power negative wife number of D. Besides, the same definition works for oriented links. If we change the orientation of the link, we only change the wife number of the diagram. Moreover, since different orientations give different wife number, the Carter-Jones polynomials of a link with different choices of orientations differ from each other by this factor to some power. In particular, when the norm of the variable t is equal to 1, let's say when t is a root of unity, the norm of the Carter-Jones polynomials is independent on the choice of orientation. So from now on, we will focus on the norm of the Carter-Jones polynomials. So far, we have a sequence of polynomial invariants for knots and links defined by some combinatoric method. However, from this definition, if the Carter-Jones polynomials of two knots are different, it is hard to tell what is exactly the difference between those knots. So we would like to ask the following question. What kinds of topological or geometrical information do these invariants capture? The so-called volume conjecture is one of the possible answers for this question. We define the nth normalized Carter-Jones polynomials of a knot K to be the nth Carter-Jones polynomials of a knot K normalized by the Carter-Jones polynomials of the unknot. Then the volume conjecture, proposed by Kashayev in 1997 and formulated in terms of the Carter-Jones polynomials by Hitoshi Murakami and Jun Murakami in 2001, suggests the following. Let K be a hyperbolic knot. By hyperbolic knot, we mean that the knot complement in SC admits a complete hyperbolic structure. And we let J pi and Kt be the nth normalized Carter-Jones polynomials of the knot K evaluated at T. Then the volume conjecture suggests that the nth Carter-Jones polynomials, the normalized version, evaluated at the nth root of unity e to the power 2 pi I divided by n, grows exponentially, and the exponential growth rate captures the hyperbolic volume of the knot complement. To compute the exponential growth rate, we consider the norm of these normalized Carter-Jones polynomials evaluated at this root of unity. Take log, multiply by 2 pi divided by n, and take n goes to infinity. And the conjecture suggests that this quantity coincides with the hyperbolic volume of the knot complement. The volume conjecture is known to be true for the frigate knot 41. Here, let me briefly discuss some ideas about how the Carter-Jones polynomials could be related to hyperbolic geometry. Given a quantum invariance such as the Carter-Jones polynomials, we first express it in terms of the so-called quantum dialogism function. When we take the limit, the quantum dialogism function converges to the classical dialogism function. And the imaginary part of the classical dialogism function gives us the Lopachevsky function, which can be used to compute the hyperbolic volume of an ideal tetrahedron. So far, we've focused on the quantum invariance of knots and its relationship with hyperbolic geometry. Actually, there is a three-manifold invariance which is closely related to the Carter-Jones polynomials. This three-manifold invariant is called the Torayev-Fierro invariant for three-manifold. Given an odd integer r equal to 2n plus 1 greater or equal to 3, and a primitive alpha root of unity q, one can define the alpha Torayev-Fierro invariance TVR MQ, which is a real-valued invariance for any three-manifold M with or without boundary. The definition of the Torayev-Fierro invariance is quite complicated. Nevertheless, when Q is equal to e to the power 2 pi I divided by R, and when our three-manifold M is actually a length complement, in 2017, Datchery, Carvagiani, and Yang proved the following results. Let L be a length in S3 with little n many components. Then, given an odd integer R equal to 2n plus 1 greater or equal to 3, the result basically says that the alpha Torayev-Fierro invariance of the length complement evaluated at this particular root of unity can be expressed as the square of the norm of the Carter-Jones polynomial of the length L evaluated at the n plus 1/2 roots of unity e to the power 2 pi I divided by n plus 1/2. Here we sum up all possible CAR such that the CAR of each component is in between 1 to n. Moreover, this extra factor μr is given by this formula. And one can show that this factor actually decays polynomially in R. In particular, it doesn't affect the exponential growth rate of the invariance. Since the Torayev-Fierro invariance is related to the Carter-Jones polynomials in this way, and for the Carter-Jones polynomials, we have the volume conjecture. It is natural to expect a version of volume conjecture for the Torayev-Fierro invariance. In fact, back to 2015, Chen and Yang proposed the following volume conjecture for the Torayev-Fierro invariance of hyperbolic three-manifold with finite volume. And the conjecture suggests that for every hyperbolic three-manifold M with finite volume, the Torayev-Fierro invariance at this particular choice of roots of unity also grows exponentially, and the exponential growth rates capture the hyperbolic volume of the three-manifold N. Recall that the derived real invariance for a length complement is related to the Carter-Jones polynomials in this way. In fact, in their paper, Dachry, Carpagiani, and Yarn proved the volume conjecture for the Carter-Jones polynomial of the frigate knot 41 at this roots of unity. That means the following equations holds. Using 1 and 2, they proved the volume conjecture for the derived real invariance of the frigate knot complement. Note that this term here appeared in the equation number 2 is only one of the terms appear in these sums in equation 1. Therefore, it is natural to ask, how about the asymptotics of the m Carter-Jones polynomials of a knot evaluated at this m plus 1/2 roots of unity? This leads to the study of the so-called generalized volume conjecture. To make things precise, we let m be a sequence in N, and we defined the limiting ratio as to be m divided by m plus 1/2 and take n goes to infinity. For example, when m equal to n, then s is equal to n divided by n plus 1/2 and take n goes to infinity. So s equal to 1, and this corresponds to the original volume conjecture. In 2017, joint work with Thomas Au, we proved that there exists delta greater than 0, such that whenever s is in between 1 minus delta and 1, or in other words, whenever s is sufficiently close to 1. The m Carter-Jones polynomial of the frigate knot evaluated at the m plus 1/2 roots of unity also grows exponentially, and this time the exponential growth rates capture the volume of the frigate knot complement equipped with the possibly incomplete hyperbolic structure, such that the logarithm of the holonomy of the meridian is given by u equal to 2 pi I times 1 minus s. If you are not familiar with this kind of notion, you may regard this as a parameterization of the space of hyperbolic structures. For example, when s equal to 1, u will be equal to 2 pi I times 1 minus 1, which is 0, and u equal to 0 corresponds to the complete hyperbolic structure. So far, this is the only result for the generalized volume conjecture for knots in S3. It will be interesting to see if we have similar phenomena for lengths in S3. To state the result, let me introduce an infinite family of lengths called the Whitehead chain, defined by Roland van der Veen in around 2009. Let A be an integer, B be a positive integer, and C and D be non-negative integers with C plus D greater or equal to 1. Then the Whitehead chain WABCD with A full twist, B belts, C clasps, and D mirror clasps is obtained by stacking these tangles together and then taking the closure. For example, if we stack one belt with one clasp and then take the closure, we will obtain the length W0110 which is actually the famous Whitehead length. And in this talk, we will also denote it by WL. And this picture shows the example of the length W1111 with one full twist, one belt, one clasp, and one mirror clasp. All the Whitehead chains WA1, C, D are actually hyperbolic lengths. That means they are complements in S3 and meet hyperbolic structures. With this setting, the first result is that the volume conjecture for the Carter-Jones polynomials of the Whitehead chain WA1CD at the n+1/2 root of unity is true. That means the following equation holds. Here we cut all the components of the Whitehead chain by n and consider this Carter-Jones polynomials evaluated at this root of unity. And this result says that the exponential growth rate also captures the hyperbolic volume of the length complement. From this result, we have the following corollary, which says that the volume conjecture for the toric rival invariance of the Whitehead chain complements is true. Here, we can put WABCD instead of WA1CD. And actually, when B is strictly greater than 1, the length complement is non-hyperbolic. Nevertheless, it contains a hyperbolic pieces in its geometric decomposition, and I will say more about this in the next talk. Next, we will consider the generalized volume conjecture for the Whitehead length. Let Si to be the limiting ratio of mi to n+1/2 for I equal to 1 and 2, where mi's are sequences in n. Then we have the following result, which says that for S1, S2 sufficiently close to 1, the M1, M2 Carter-Jones polynomials of the Whitehead length evaluated at the n+1/2 root of unity also grows exponentially, and this times the exponential growth rates capture the hyperbolic volume of the Whitehead length complement equipped with the possibly incomplete hyperbolic structure such that the logarithm of the holonomy of the meridian of the belt and that of the longitude of the clasp are given by u1 equal to 2 pi I times 1 minus s1 and v2 equal to 4 pi I times 1 minus s2 respectively. Finally, we generalize this result a little bit to a special case of the Whitehead chains as follows. For the Whitehead chain W01C0, we color the belt by M1 and all other components by M2. The following picture shows the case of the length W0120. We color the belt by M1 and all other components by M2. Then the exponential growth rate of the Carter-Jones polynomial of the length W01C0 at this root of unity also captures the hyperbolic volume of the length complement in the same spirit as the situation for the Whitehead length. That means for the belt, we have the equation U equal to 2 pi I times 1 minus S. And for all the other components, we will have V equal to 4 pi I times 1 minus S2. That's the end of this talk. In next talk, I will discuss what happens when our lengths and V manifolds are non-hyperbolic. Thank you so much for your attention.